Hey everyone, in this video we're going through the solutions to the VCA methods sample exam number 2. So these are only sample questions, not indicative of what the actual exam is going to be like in terms of length. And also we know in exam 1 we saw Newton's method of approximation. We're also seeing it here. So whether it's going to be on both exams is hard to judge. But if it's not on exam 1, it'll definitely be on exam 2. So they'll definitely assess it. But it could also be on exam 1, like we saw in the sample questions for exam 1. Anyway, let's make a start. So it's a longer exam, so this is probably going to be a longer video. I've already done the solutions. Now, if you get a little bit bored and you're like, oh, I'm just going to correct from the solutions, or I'm just going to copy down the solutions, you're not going to learn that way. You really need to listen as I work through the questions, unless you've done them already yourself and you just want to correct them and you get 100%, good on you. All right, so let's make a start. So question number 1, we've got 2 equations there. Which one of the following correctly describes the general solution to the system of linear equations above? All right, so when you're solving equations, the number of unknowns you have is how many equations you need. So we can see in this question, we've got x, y, and a z. It's a little bit faint, but you should have the questions in front of you anyway. So if we were to solve for x, y, and z, we would actually need 3 equations. But here we've only got 2, so that's why we have a general solution. So it just means that we have to allocate a letter to one of these variables, x, y, or z. Now, you may have seen questions before, because I know I've done them, in terms of lambda. So lambda is just a Greek letter, just like pi is a Greek letter or theta is a Greek letter. Now, in this question, it's multiple choice, and they've allocated, as you can see, x equals k to every single one of the options. So we're going to say, all right, we know x is equal to k, so we're going to use that knowledge to get y in terms of k and z in terms of k. So your calculated notation is here, and I've already done this, so let me just scroll through, go back to main. All right, so now my calculator and my computer are not cooperating. Do you want to stop? No, it doesn't want to stop. Oh, where are you? Okay, there we go. So you'll notice how I've done x equals k, x minus 2y equals 3, and 2y minus z equals 4, and then we're solving for x, y, and z. So it's just a matter of interpreting what the calculator has done, and if you want to get it in standard form, I had it in decimal before, but you can change it to standard form. Just make sure you can interpret what the calculator has told you, because it might not always match what the multiple choice options are. All right, let's move on to the next one. Now, this is my second try at this video, because my calculator is playing up and it annoyed me so much that I deleted what I did. So, yeah, I might have to flip my laptop if it keeps annoying me. All right, question number 2, we've got a Newton's method of approximation. So this is a different type of question that we've really seen before, and I'll show you in a sec how to do it on your calculator. So we're going to actually I should read the question, Newton's method is being used to approximate the non-zero x-intercept of the function with the equation blah 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 with an initial estimate of x naught equals 1. So Newton's method of approximation, it'll give you an initial estimate. So in this case, it's 1. So we've got to use that knowledge to apply Newton's method of approximation. Now, if we're gives the first estimate that would correctly approximate the intercept to 3 decimal places. So basically that means we're going to keep going through iterations. So x0, x1, x2, x3, x4, x5, and so on, until we get an estimate that we keep getting the same answer to 3 decimal places. Now, if we did that by hand, and you can see there we're going to be doing 8 iterations. it's quite time consuming to do by hand, so you wouldn't be expected to do that many iterations by hand. But you can see on the previous, exam 1 sample questions that you do need to be able to do Newton's method by hand, but not too many iterations. So with Newton's method of approximation, we do have the formula on the formula sheet. So here it is. So with your function, you just need to know the function and its derivative. So if I get my calculator up, and I've already got stuff written in here because it was annoying me before. So you can see I've already defined the function and found its derivative. So I've got my function and its derivative already in my calculator, but you might not already have it in your calculator, so you'll need to put it in there. Now, you can keep doing iterations on the home screen. It's just very time consuming. So in your calculator, if you go to the menu and go from that screen across to sequence, and you can see I've already tried to put it in, so I'm going to clear that because it was not cooperating with me before. And we're going to put this formula in here. Now, I couldn't use f of x when I was defining it, which was a bit annoying. So I don't know whether it was me or the calculator doesn't do it. So instead of xn, I'm just going to use an, because you can see that's the variable in the question, but just make sure if it was not a multiple choice question that you don't leave your answer in terms of an, it is xn. All right, so I'm going to copy. Now this didn't like me doing this before, but let's see how I go. Whoops. All right, so I'm just going to copy that. Looks like it's kind of cooperating so far. I knew it. All right. This is where I get serious and I open up my laptop. Now, it didn't like me going from one screen to the next. So if I go back to my main, and instead of copying and pasting, I'm just going to have to write them out. Now, did I write it on my other sheet? No. And I did these questions a while ago, so I'm trying to remember how I did it. But I'm pretty sure using f of x didn't work for me, and it didn't work before, but you know, I haven't played around with it much since. So I'm just writing down f of x and its derivative on a sheet of paper, so then I can copy it down. All right, it's a bit annoying that I can't just copy and paste it. Actually, oh no. It will paste, it will copy and paste, but as soon as I leave that sequence screen, it doesn't stay in there, which is really annoying. Okay, let's go back. Actually, maybe it would have. I think it actually would have. It was because I didn't actually put anything in those boxes. Anyway, let's write it down. Okay, so we've got x cubed over 5 minus the square root of x. So, oops. So that's my f of x. Now, because my my formula is in terms of an on my calculator, I'm just going to change that x to an. And then on my denominator, I've got 6x to the power of 5 on 2 minus 5 over 10 root x. Now again, it do the same thing, and I could have done it before, but sometimes talking and looking at a piece of paper and typing on the computer distracts you. All right, so just make sure everything is in there. I think I've also done in the when I did this previously, I left it as x, and then I did given that x is equal to an. All right, so I'm going to tick the box, and if I go to just up the top corner where you can see a little table, oh, I think I've made a mistake somewhere. All right. I'm going to pause and just see where I went wrong. All right, basically, just as I pressed pause, I knew what I did wrong. A0, I haven't told it A0 is equal to 1. Okay, so it might be a good idea to write down what I've just done, because now when I go back to here, you can see it has now done those values. So you can see each iteration. So we start off with 1. After 1 iteration, we get 9. After 2 iterations, we get 6.0516. So it just saves you time doing all the iterations. It's probably not going to be a question that's going to help you with pseudocode. It could be depending on what the question asks you in pseudocode. So basically, we want to know to 3 decimal places. So you can see that at iteration 8, all right, we're getting the same. So 9037, 9037, 9037, 9037. So it is, and if we're doing, it's to 4 decimal places there, but we're only doing it to 3 decimal places. So at n equals 7, we're at 905, but then we go on to 904, 904, 904. Because you're approximating it, these decimal places do continue. Now, if you want to, so let's say, not that one, sorry, this one here. Okay, let's say you had settings in your calculator and it stopped at n equals 5 and you haven't seen your answer. So it's just this XY button up here, and you can change the iterations. And also if you had to go to a higher one, you don't want to start at 1. So I went as high as 15. I don't know why. I only had to go as high as 9. And if I go here, no, I don't think this is going to help us. Just wondering if I can change it for decimal places. Okay, I thought that would happen. All right, so you can see when I highlight the number down the bottom, you've got your more decimal places. So you can see at iteration 8, all right, the 9037 they're not the same number as I keep going. All right, but it's getting closer and closer. So if we wanted it to 3 decimal places, and let's say you couldn't, maybe say you wanted it to, I don't know, 5 decimal places, and you can see it's not on there. You can actually just hover to get the actual answer. So the 90365, all right, so that would probably be the 9th iteration we would need. All right, if we were doing it to 5 decimal places, but we're just doing it to 3 decimal places. So it's iteration number 8. So X8. All right, so make sure you're familiar with how that sequence works. Put that question in your bound book, okay, and the same notation. And make sure you put in your initial value. So remember, I didn't do that and I came up with all those zeros. That's because our initial value was 0. And it told us the initial value was 1. So that was why it was 1. All right, so let's move on to question number 3. So the area, blah, 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 and the x-axis, blah, 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 has been approximated using the trapezium rule. Using the trapezium rule, the approximate area calculated is. So when you're doing approximations with the trapezium rule, you've got the formula sheet. So it's not just a matter of doing, and I'm going to start writing again, because sometimes I think I talk and it's easier if I actually show you what I mean. So the area of a trapezium is a half a plus b times h. So because we're looking at trapeziums like this, this is your A, this is your B, and this is your height. Now, with your formula sheet, the formula is obviously not written in that format, so you need to be familiar with how to use the formula on the formula sheet. So I've done a video on that, and instead of telling you again here, you can just go back and watch that watch that video. But I just basically did a process of elimination for this one, and this is the sort of question you could probably do in reading time if you had some spare time. So your first line and your last line are only included once. All right, so it's only included in the first trapezium, and the last line is only included in the last trapezium, whereas this second line is included in the first trapezium and the second trapezium. We're calculating it twice. So when you're calculating the area of a trapezium using the formula, you'll see that your, well, in this case, we've got half. So you've got f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus 2, oops, not 2, just 1 f of 4. Okay, because f of 0, where x equals 0, and where x equals 4, that line is only counted once, but everywhere else we multiply by 2 because the line is included twice. So when I did this question, I didn't even bother looking at the formula sheet. I just first of all made sure everything was a half at the front because this length is 1, so it has to be a half. And then your first value I can see, so f of 0 is at 4. So that meant my first value had to be 4. So immediately I could eliminate C, D, and E. Now that's assuming that the numbers are written in order, which they probably would. I don't know why they would want to confuse you like that. And then I thought, well, what else can I see? Well, I can see it f of 3 is equal to 1, and that line is included twice, so 2 times 1 is 2, so there's your answer. And that sort of question, if you're quite confident, could easily be answered in reading time without the use of a calculator. But obviously you can't write the answer there, but you know, you could have other ways of remembering. All right, question number 4, the probability density function of f, blah, blah, blah. The value of a such that probability of x is less than a equals 5 over 8 is. Okay, so we've got a piecewise function here. So we've got, when x is between 0 and 4, we've got that function, and then from 4 to 7.2, we've got that other function. So I just did the definite integral from 0 to 4 because we want to know 5/8, which is 0.625. So you can do this actually on your calculator as well. But yeah, if you were doing it by hand, just finding out which interval we're looking at. So 0 to 4 is 0.6. So that means A is within this interval here. So I'm now going from 4 to A, and we need to find that upper limit. And we're using the second function that you can see here. Now, because this first one was equal to 0.6, that means your second definite integral has to be equal to 0.025. And I get 2 answers for A. All right, and I haven't restricted my domain, so I could have restricted it and said that A was between 4 and 7, and then you would only get one solution. You could also see how it's in exact form. You could put it in decimal and know that you can't be greater than 7.2. So that would help you choose the right one, because as you can see, both the positive, so here's your positive version, here's your negative version, they're on there. So you do have to check which one fits. So it is C because it is less than 7.2, which we want. I think the other one was like 10 point something. All right, so also can be done on your calculator with a solve. All right, now we've got a pseudocode question. All right, the algorithm below described in pseudocode estimates the value of a definite integral using the trapezium rule. All right, so I don't think you would see trapezium like the question above and then trapezium in pseudocode, but you never know. All right. So always take note of what is being defined. So A is your lower, B is your upper, and N is your number of trapeziums. And then it's usually defined down here. So f of x is equal to log base E of x, a is equal to 1, b is equal to 3, and n is equal to 10. So make sure you can interpret that as well as do the pseudocode, because as we're seeing with other questions, it's sometimes just interpreting things like that. All right, so the value of variable sum after one iteration of the while loop would be closest to. So we're only going through it once. So we've got all these values being defined here. So we've got h, all right, we've got the sum, and we've got x. So if I'm doing, so you can see down here in our while loop, all right, we've got to do this sum plus 2 times f of x. All right, and I've written it down here, sum plus 2 times f of x. And so you've got to say, well, what is the sum? Well, the sum has been allocated f of a plus f of b. So there. And then 2 times f of x. So f of x is log base e, and x is a plus h. So that's why there's a plus h here. And then what is h? This is h. So you've got all of it defined, but it's not in a user-friendly way. So it's just a matter of, I suppose, putting things in, substituting values in, working your way until you actually know, because the only values we know are a, b, and n. So basically we want an equation just in terms of a, b, and n, or f of a and f of b. Now you can use define on your calculator, because f of x is log base e of x, and put all those values in. So you can see there's my a, there's my b, here's my a again, and then this is my b minus a, and then we've got to divide by n. All right, so I've just substituted my a, b, and n into that equation. You can do that on the calculator, and we get 1.463. So we've just done one iteration, quite a lengthy one to do, so I wouldn't be surprised if you only did it once, maybe twice, but definitely not more than that. All right, moving on to question 6, so another pseudocode. Again, I don't think you'd get more than one pseudocode question on multiple choice, but you never know. All right, so we're doing bisection method now. So bisection method it's not on your formula sheet, but it's not that hard. You just add 2 numbers together and divide by 2. So you can see here, add 2 numbers together and divide by 2. So we've got f of x, and it does tell me that f of x is in radian, so that must mean it's a trig function. Yes, it is sine x. So just make sure that your calculator is in radian mode. Now you might need it in degree mode if you're relating tan theta to your gradient for a different question. It's probably the only time, but don't think that your whole exam is going to be in radians. You might have to use degrees. And I've done questions where you've had to put it in degrees. All right, so a is your lower interval, which is 3. Actually, it's defined the function here. B is 5, so f of x is sine x. A is equal to 3, b is equal to 5, and max number of iterations you're going to do is 2. So it means we go through the while loop twice. All right, the value that would be returned when the algorithm is implemented. So here we've got to go through it twice, so the maximum is 2. So you can see I've done that twice. So my first one, I get a, all right, actually so we've done so many of these, but I'll do this one again. All right, so your a plus b. So for the first one, our value of a is 3, b is 5, and divided by 2 gives us the midpoint of 4. Then we've got to check whether where this midpoint is. All right, so we just do f of 3 times f of midpoint, so this section here. Now, if it's less than 0, then we allocate B to the midpoint. If it was greater than 0, then we allocate A to the midpoint. So it is less than 0. I did it on my calculator. So our B now becomes the new, so the midpoint now becomes B. So B before was 5, now it becomes 4. So we will start the process again. A plus B divided by 2. A stays as 3, but B changed to 4. So please, 3 plus 4 divided by 2 is 3.5. And that's our second iteration. So that's why we stop at 3.5. And I think I've done that question before. Oh, we got another one. Okay, so this one is different again. And we've got Newton's method of approximation. This time we're looking at tolerance levels. So remember when we did it on the calculator? All right, so it's basically just how many, the difference between the two x-intercepts. Sorry, not x-intercepts, the two x values that we got. So let's say x of n plus 1 minus x of n. All right, so we want that to be less than 0.001. All right, so the difference between the two. So this is our next, and this is our previous. And so here we've got, I'm just thinking what I'm reading. So we've got Newton's method, we've got a function, f of x. I don't think it really matters what f of x is in this one because we're only looking at tolerance level. And x0, don't think we've assigned a value to, so probably just the initial estimate. So we've got our derivative, and so we're probably just starting at 0. So it doesn't really matter because we're working in terms, not in terms of a function, but just in terms of the Newton's method of approximation in general. So here's your formula. All right, and I've just realized I've written it incorrectly. So I had to pause just to check. That should be xn there. All right, so, and this should be x of n plus 1. So basically what this is saying is your next value, so this is your next value, is equal to your previous value here, so your xn, minus f of xn over or divided by your derivative of xn. All right, it is just your, it's just Newton's method of approximation written in pseudocode, well, not pseudocode, but written across the page for pseudocode. All right, so what we want to know is we want it to have a tolerance level of 0.001. So you can see in all our answers, you've got that 0.001. You've just got to understand how to get that tolerance level. So we want next minus previous. We want the difference between our two estimates to be less than 0.001. So I'm going to cross out any that don't have next minus previous. So I'm going to cross out C because it's previous minus next. And because your two values could also be negative, we need both negative 0.001 and positive 0.001. All right, so we're just going to cross out A and cross out B. So it can either be D or E. Now with Newton's method of approximation, we're basically calculating, remember we're doing x of n plus 1. So this is your formula. This is your next value. So basically it's returning your next. So your correct answer is E, whereas in part D, it returned previous. So we don't want it the previous value, we want to know the next value. All right, so good question to have on your formula sheet as well. All right, so now we're looking at the extended response questions. Just going to have a quick drink of water. All right, so here we've got to sketch the graph of G. Just take note of this restricted domain. And it has, so when we're sketching it, we have to label the asymptote with its equation. All right, so you can see I've done that there, x equals 0. So it's x equals 0 because our argument there cannot be less than, has to be greater than or equal to 0. Sorry, not equal to, has to be greater than 0. Has to be greater than 0, so your asymptote is at x equals 0. It can't hit x equals 0 and it can't cross x equals 0. We have to label our axes intercept, so you can do that on your calculator. Just type it into your calculator and get those axes intercepts. It does say correct to 3 decimal places, so that's awesome. Just make sure if you're using the graph screen, and I wonder, I don't think I have, let me just check whether I've already got it sketched. No, what was I sketching there? When you're doing it on the graphing screen, just make sure that it does, actually I might show you what I mean. So if we're sketching this, x minus x. All right, so you can see the graph there, and if I want to do those x-intercepts, so sketch, oops, sorry, G-solve, let's get back on. Oh, I do not know why I did that. Oh, that is so frustrating. I think I touched the wrong sheet. There we go. Oh my gosh. G-solve, so root, and you can see next to the cursor, it's got it there, but down below, just at the bottom of the screen, you can see it's to more decimal places. So depending on how many decimal places you need to round it to, kind of look at that number as opposed to the number next to the actual graph. Down below is better. Now, if you had to have the exact value, so I'm just going to copy that. Go back to my main screen. If you needed the exact value, just go to solve and let it equal 0, comma x. Oh, okay. All right, it's giving me not exact values anyway, so it's actually giving me the decimal places. But if you had to have an exact value, then you need to do it on this screen. It won't do it on your graphing screen. And you can see there I've got my 2x intercepts anyway. And you can do your, what are we doing now? Our max. Oh, what did I do wrong? I think I pressed it twice, didn't I? All right, so you can see there it's given it to me in exact form. So if I want the approximate value, you just go there and just rounding correctly to 3 decimal places. All right, you can see some other lines on the page. That's just because later on I have to draw tangents. Just make sure if you're drawing anything on the graph that it's clearly labeled. Oh, and also you needed that endpoint. So just going back to my calculator. So you can just paste. All right, and then give it, oh, come on, cooperate. Given that x equals 7, so that's our endpoint. And because it's decimal places, just change that to decimal. And there you can see that endpoint. So putting that endpoint in as well. So 3 marks, I would say that would be 3 easy marks because everything can be done on your calculator. You just need to remember that asymptote and the endpoint. They're probably things you would forget. All right, find the equation of the tangent. So easily done. Oh, sorry, wrong button, on your calculator. So interactive calculation, go to line and then tan line. All right, so pasting that expression again. So you could define it, oh, I've just copied it, and we wanted x equals 1. We go 2x minus 3. Just make sure you write y equals, because it's an equation, not just 2x minus 3. All right, sketch the graph. So I've sketched it. Now it doesn't say to label anything. I'm quite surprised. I wonder if that is an oversight when writing that question. But you can see I've drawn this is the first tangent here, and I've just included that at 1, -1, to show that was, yeah. But you can also do that on your calculator. All right. Newton's method is used to find an approximate x-intercept of g with an initial estimate of x0 equals 1. Find the value of x1. All right, so again, just using Newton's method of approximation. So we want x1. So x0 is 1. So 1 minus f of 1 over your derivative. All right, you can do that on your calculator. You can also do that one by hand. It's not a hard one to do by hand. Oh, and your gradient is here anyway. So I think that's why I didn't actually do any working out for that, because I saw that. All right, going down. Find the horizontal distance between x3 and the closest x-intercept. So again, we're using Newton's method of approximation. So I did x2 and then x3. You don't have to do all that working out because we only need x3. You could do the sequence like I showed you before. Just make sure you put in the correct values for g of x and g dash x. So x3 is equal to this. So we had the actual the actual x-intercept minus our approximation, x0, and there's the difference. Find the value of k where k is greater than 1, such that initial estimate of x0 equals k. Gives the same value of x1 found in part C. Give your answer correct to 3 decimal places. All right, so here we don't know our initial value. So I'm actually quite glad this question's in here, because this is another way of using Newton's method of approximation. So we don't know what k is. So I've just substituted k basically in for x0. All right, so put those in. On your calculator, you can get your function, and I shouldn't have written f, I should have written g. Oh, oopsies. Don't think could have been penalized. I'm going to say just be safe, do be consistent. So it should have been a g. And the value, the approximate at x1 we found out before was 3 over 2. So I got that from part C. So in my calculator, you can just solve that. All right, so solve, putting that in where k is greater than 1. So we get k is equal to 2.397. So just using solve on your calculator for that. It is worth 2 marks. I would say 1 mark for that. And then 1 for your answer. Don't use calculator syntax either. So don't go putting, solve, blah, 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 comma, k. All right, just pretend you're not using a calculator and just write the equation down. All right, and then we had to sketch that. So I've sketched that tangent on the graph. So I'll just go back up. All right, so that's my other one here. What did I do? I can't remember now. Find the value of k. Using the value of k, sketch the tangent. Oh, okay. So I just, substituted that in. And I'm just wondering what I've done here. because that doesn't look good to me. Oh, actually, no, sorry, I thought that was a point on the line. That's my turning point of my graph. All right, so I've just sketched the line. I haven't actually added any points in or anything. So if you had to sketch a graph and it didn't ask for anything, don't think you have to put it in, but you do have to have pretty accurate x-intercepts and so on. All right, so make sure you x-intercepts and y-intercepts, and it has to hit the graph at the right point. All right, scrolling along because my computer is nearly out of battery. All right, so question number 2. So Jack and Jill have built a ramp for their toy car. They will release the car at the top of the ramp and the car will jump off the end of the ramp. The cross section of the ramp is modeled by the function, blah, blah, blah. So we've got f equals 40. So you can see here from 0 to 5. And then the rest of the graph from 5 to 55, we've got that function. It is continuous at x equals 5. So if it's continuous at that point, it means it's differentiable at that point. And I don't think I'm going to get this done in time, but we'll keep trying. All right, so there's the graph. Okay, so you can see that where I've circled, it's a bit of a straight line. So just picture Jack and Jill rolling their toy car down that. All right, so we have to find the derivative. So we're finding the derivative of each function in that piecewise function. So the first one, we're doing f of x equals 40. So the derivative of that is 0. And then the second one. Now you'll notice we have to stating our values of x because it's different depending on where we are. So for the first one, we're going from 0 to 5. You'll notice I have not included 5 in there and I've included in the second one. So just including it once. And we don't include the endpoint, so we can't find the derivative at these endpoints. So you can see that they haven't been included. All right, so if you don't get those domains correct, you'll probably only get 1 mark for that. All right, find the coordinates of the point of inflection of f. So points of inflection and stationary points, we have the derivative is equal to 0, which is quite easy. You can just do that on the calculator. Just make sure it does state the coordinates, so you do have to write the coordinates. So 25, 20 are your coordinates. Find the interval of x for which the gradient function of the ramp is strictly increasing. All right, so with your, I'll just go back here. So our point of inflection was at 20, was it 2025 or 2520? 2520. So 2520, yeah. All right, so basically your graph is decreasing. All right, so at that point, and then it's increase. It's a positive. So decreasing, so it's a negative graph and then it's a positive graph. So from 25 to 55, it is strictly increasing. And then from 5 to 25, it's strictly decreasing. All right, so you can see what is happening with either side of that point of inflection. So if you're concave down, like we are here, concave down, which kind of goes like that, it's strictly decreasing. And then concave up, can't spell, strictly increasing. All right, so when we're including those values, when we're doing our domain, we include the values. All right, so strictly increasing from 25 to 55 and including those values, and decreasing from 5 to 25. All right, I'm sorry I'm rushing, but not only is my battery running low, I've also got a dance class to get to. Okay, so Jack and Jill decide to use 2 trapezoidal supports, each of width 10 centimeters. So you can see here we've got a width of 10. All right, so I've labeled it area 1 and area 2. So two trapeziums, I've just used the formula I showed you before. So area equals a half A plus B times height. Now you can use that, or you can use the formula on your formula sheet. I just think for two trapeziums, easy just to do it like that. We have to find the ratio of the area of the trapezoidal cross section to the exact area, and it tells us to give the answer as a percentage. So we're just doing our approximation, which is here. We also have to work out our exact area, which was easy to do. It's just a definite integral. Just make sure your definite integral, we're only going from 5 to 25. All right, but you can do that on your calculator. All right, and we get 98.1%. So 3 marks. I actually think that's an easy 3-mark question, which would be great if you had that on your exam. All right, question D, referring to the gradient of the curve, explain why a trapezium rule approximation would be greater than the actual cross-sectional area for any interval P to Q, where P is greater than 25. So here we stopped at x equals 25, and remember I said that's concave down. When you're concave up, your trapezium's going to be above. So if I drew that, it's going to be, oh, that's terrible. All right, slightly above like that. All right, so my answer, yeah, basically talk about it being strictly increasing and concave up. Oh, I'm coming. All right, last question, I think. Let's quickly do it. All right, so setting, because actually, you can read it yourself. So because the graph is continuous, so f of x and g of x both share 55. So f of 55 is 8.75. That means g of 55 is also 8.75. And the derivative at that point is the same. So you can see there that I've made them equal. So just putting that into your calculator. So putting these two into your calculator, and you can solve for B and C. And I've given 2 answers here. So my first one, this one here, just notice with no roundings required. So if you're not, if you're giving an answer in decimals, just keep going until your decimal points end. So C can be written like this because it's a terminating decimal, but you need to include all 4, or you can put it as a fraction, which is fine. All right, and then the last one, determine the horizontal distance from the end of the ramp to where the car lands. Okay, so G of A equals 0. So you can just do that in your calculator. We get 2 values for A, so just make sure you're selecting the appropriate one. So A has to be greater than, what was it, 55? I can't remember now without scrolling. Yeah, 55. So the ramp ends at 55. So the difference between A and 55 is just here. So here's your value of A, and then you're subtracting the end of the ramp, which was at 55. So the difference is 34.10 to 2 decimal places. All right, guys, I'm going to have to end there just because my battery's dying and I've got a dance class to get to, but I hope that was helpful. Bye.